On finding the area between two curves, and in this particular video we're going to talk about a situation where we do not have bounded lines, meaning we don't have this second part here, which is x equals and x equals. You notice all we have are two functions, okay? And so what we're going to deal with here is that the actual bounded lines, or where the our region is bounded, is by those intersection points, which is emphasized in this situation right here. So this is a situation we're talking about for this video. So now let's, I start out with the same steps I've always done, which is set the two functions equal to each other to determine where they intersect. So these are pretty unique functions, so we're going to walk through how we're going to solve where they intersect at. All right, so we got x squared over 4. Okay, now at first glance this thing, I don't like it. I got a divided by 4, I got a radical here. Let's start out by just eliminating this 4 on the bottom. So to do that, I'm going to take both sides times 4. And you can do that because things stay equivalent as long as I do the same thing to both sides. So now I have 8 square root x equals x squared. All right. And because we have a squared function here, we're going to get everything over to one side or set it equal to 0. In this case, again, this is kind of a unique term here. So what I'm going to do is I'm going to subtract the 8 square root x and put it over on this side because I want to keep my x squared positive, okay? So I'm going to rewrite this and just kind of put it on this side. So we would see x squared minus 8 square root x equals 0. You could also have 0 equals this, but I did this because for me it looks a little bit more if the stuff is on the left equaling 0, okay? So what I'm going to do is kind of a unique situation. We've never really dealt with this before, and that's where we have a radical as one of my terms. But I can simply do the same steps I would normally do. I'm going to factor out a square root x. Okay, so that's essentially like saying factoring out a x to the 1/2. All right, same thing. So what this is going to leave us with is x to the 3/2, or 1.5. So I took a half away from this. Because remember, when I multiply two things with this same base, then we add their exponents. So this would result, if I were to multiply this back out, x squared. All right, so now I've got to solve this little problem here. So we know this, to make square root of x equals 0, all we have is x equals 0. So there's one of my intersection points. And to find the other intersection point is I have to solve this problem. So what do I got to plug into x to make this little piece equal 0? Right, so I follow my steps here. I'm going to say plus 8 plus 8. So then I get x to the 3/2. Now, the 3/2 can be a little bit like kind of eye-catching in terms of solving a problem here. I got x equals 8, but 3/2 might be a little bit intimidating. So what I'm going to do is I'm actually going to write it as in radical form. So that would be the x to the 3rd squared divided by 2 would be the same as x to the 3rd, the square root of x to the 3rd. So now I can use my tricks here to solve this one. So if I square both sides, x to the 3rd equals 64. Opposite, or the inverse of cubing something, is to cube root it. And so I get x equals 4. Okay. You could have also taken 8 to the power of 2/3, and you'd end up with the same thing. But okay, so we have our two intersection points. We have one at 0, and we have one at 4. And as I've done in the past videos, I'm going to write those right up here. So my intersection points occur at x equals 0 and x equals 4. Okay? So because this is our first time dealing with this situation, I'm going to show the graphic early this time, just so you can see what it will look like, and I'll kind of break it down a little bit. So, within this intersection points, we have 0, 4. And again, as we've talked about the part B here, that's going to make up our boundaries of the region. Okay, so let me show this graphic real quick to kind of help visualize what we're accomplishing here. Okay, so here is the, I'm going to make it a little bit smaller here. So here's the actual graphic that we're finding the area for, the region we are finding the area for. And you'll notice that it has an intersection point at 0. Right here, and it has an intersection point at 4, and that enclosed area makes up the our region we're finding the area for. So we just got to kind of go about our steps here. We got to figure out which is the top function. Now you may be able to see here that this looks like the top function, which would be this 2 square root x. But for the purpose of showing you how it works here, we're going to have, I'll call that, like I've been doing, f of x, and I'm going to call this function g of x. All right, so I got to pick out a number to plug in. Let's say I'm going to plug in, I got to figure out who's enclosing the top. And again, because we have the visual here, I could just visually see it. But again, for the purpose of what we're trying to show here, let's pick out a number between 0 and 4. I'll pick 1 because that seems pretty nice and easy. So let's see. So if I plug in 1 into this function, I get 2. If I plug 1 into the g of x function, I get 1/4. Okay, so that means that my top function, or the top of my function, is this one because it produces a higher value of 2. So with that information given, that means I'm going to have f of x minus g of x because the top function, or the one that encloses the top, goes first. So we got f of x minus g of x, and then I'm going to write this out. So I have 2 square root x minus x squared over 4. All right, and now I got to take the definite integral of that. So I've got it all set up here, and I'm going to find from 0 to 4 because that's the enclosed area based upon these right here. Okay, so now I'm going to take the indefinite integral of this, well, ultimately definite integral, but I got to still figure out what this is. So let's see, 2x to the 1/2, and I'm going to rewrite this as 1/4 x squared. Same kind of thing, so I'm still working on the integral here. And so that would be, if I were to write it all out, that would be 2x to the 3/2 over 3/2 minus 1/4 times x to the 3rd over 3. Okay, so if I clean this all up, it's kind of a jumbled mess right now. I would have 4/3 x to the 3/2 minus 1/12 x to the 3rd. And I still got to take the definite integral, right? Okay, so just to double check my work here, I think I'm good. All I did, remember, with the indefinite integrals, I just moved this denominator up, so multiplied the coefficient in front. So we got 4/3 x to the 3/2 minus 1/12 x to the 3rd. So now I just got to do my fundamental theorem of calculus. So I got, let's see, capital F of 4 minus capital F of 0. Okay, to speed up time a little bit, I did put those in my calculator. So F of 4 is 5 1/3. Okay, minus, if I plug 0 into this, it's going to produce 0. And so my area of this little space right here is 5 1/3. Or you could say 5.3 repeating. All right. So again, the graphic there kind of shows, remember we talked about the enclosed top here is the one that goes first. So that would be this function. That's why we chose this function first. And then this bottom one was my g of x right there. So that one enclosed the bottom. So that's why that one went second. All right. So hopefully this video helps you out. I'm going to do one more video of what happens if we do not have bounded by x and x, and then we have, let's say, 3 intersection points. So that'll be in the additional video. So thank you, and please email if you have any questions.